Okay, so I want to just go through a summary of quantum mechanics, the stuff about the adiabatic theorem and all that. Okay. So where we start off with, very roughly speaking, is we start off with a classical analog, right? We start off with the classical problem where there's a Hamiltonian, right? And it might model something like a simple harmonic oscillator, but it changes in time. Okay, and the change in the Hamiltonian with respect to time actually turns out to be just the derivative of h due to explicit time dependence. You see, there's this convective term which vanishes because of, well, essentially because of Liouville's theorem. Okay, so, there's the dH by dr plus dH by dP times p dot, right? And using Hamilton's equations, you can show that these guys vanish, okay? And essentially, I'll skip this bit, roughly speaking, but essentially the energy changes in time, and omega changes in time slowly as well. But the key result, the key piece of physics is in realizing that actually I of t, right, this thing called the adiabatic invariant, which is the energy as a function of time over omega of t, varies very slowly. Very slowly. Okay, so this is under the condition that d omega by dt times by 1 over omega, which is how much the angular frequency changes over a period, roughly speaking, is much less than whatever the angular frequency is at this moment. Okay? And when you calculate I of t, you get another factor which actually leads to a really ridiculously small quantity for the rate of change. I'll go into that some other time. Then there's this phase space interpretation. Okay, in phase space, the simple harmonic motion is an ellipse. Okay, and it's got, let me call this distance A and let me call this distance B. And A is given by 2me. So these are the semi-major and semi-minor axis, and 2e over m omega squared. Now this ellipse actually changes, well, A and B change in time, so we get different ellipses over time. Notice that actually a condition of adiabatic, the fact that the change is adiabatic, is that, by the time we loop around, the ellipse basically shouldn't have changed that much shape at all. Right, it changes very gradually in comparison to the period that it takes for this oscillation to take place. So, if you were to really speed up time, the particle trajectory might look something like this, and it will eventually maybe change into something like that, very gradually. Okay. So now, if you ask about the area, okay, the area which is incidentally given by this integral, this contour integral, okay, it's pi times a times b, which is nothing but 2 pi times the adiabatic invariant. So this says that the area changes very slowly, so it basically remains a constant. Okay, and also we basically got this from, you can see a similar thing when you use the Wkb approximation. Now in quantum mechanics, right, the Wkb approximation comes in, and you can see that actually the area is related to a quantum number for the harmonic oscillator, or alternatively E divided by omega, since E is h bar omega times n plus a half, you get that this quantity is essentially related to a quantum number. And the Adiabatic theorem essentially says that these energy levels, that the quantum level doesn't really change in time. It changes very slowly. So it tells you that your probability of transitioning is very, very, very slow, right? It's very, very low. Okay? Now, if we go back to what we did in perturbation theory, can remind ourselves that the probability of transition, these are all about essentially motivating the adiabatic theorem. So we had this result, and this result was for a constant perturbation, delta H. And notice here that the probability is very low. It's lowered down due to this suppression of this 1 over omega, where omega, the difference between the energy levels must be substantial enough. That's the important thing, right? We're not assuming that we're in a continuum of states, okay? And also, even if this isn't made to change in time, the only way that you can get an appreciable change in the only way where you can get an appreciable probability of transitioning is if the perturbing Hamiltonian oscillates at a frequency that's essentially comparable to the difference in the energy levels, right? This is exactly pretty much a photon coming in and exciting an electron, and the incoming photon must have, an energy that matches h bar. The incoming photon must have a frequency whose associated energy must match the energy level of the difference. So if you've got a slowly varying perturbation, you can be assured that the probability of transitioning is really slow. But this is we really want to dig into the subtleties, right? We don't want to just leave it as saying that, well, if you are in an energy level, you're probably going to remain in that energy level. We really want to understand how all this works. So, but the key message is that it is difficult to change energy levels for a slowly varying process. Okay? Now, we get into the idea of adiabatic evolution. Okay? So, the idea is that if we begin in a quantum state, right, which is one of the, if it turns out that we start in a quantum state that's one of the eigenstates of the Hamiltonian, will most likely, or incredibly likely, will remain in that state. But the wave function evolves in time, right? It's just there's a phase factor, right? And the interesting thing is that you might be tempted to say, oh, the wave function just varies, the wave function just varies as something like e to the I energy over h bar times t. But this is no longer true because the total energy is varying, right? So if you remain in the same state, it's not the phase is not going to evolve as simply as this. Instead, we're going to pick up an extra phase factor, which we call the Berry phase. Okay, that's due to Berry, B-E-R-R-Y. Okay, so if we delve into the maths, okay, I'm going to just delve into the summary of the maths. Right, so what we start off with, well, one of the things we start off with is saying, okay, let's say that psi of t is an eigenstate. Now, of course, the notion of eigenstates is you have to be a little bit careful, right? Because now that the Hamiltonian is time dependent, the eigenstates are going to depend on time as well. So at a fixed time t, instantaneously we can make sense of this equation, right? The energy eigenstates are all, understandable. But as we evolve time, the energy eigenstates are going to change. However, the energy eigenstates are going to change rather, very, very slowly, very smoothly. So it might do something like this. Now, there's obviously the very real possibility, the real concern that the energy levels might actually cross over, but we're going to ignore that, right? We're going to assume that they're going to all stay pretty much well separated. Okay, so over a really large time scale, the energy levels might look like this. Now, the idea is that if we start out in an energy eigenstate, we're basically going to remain in it with a very, very small transition probability. And the phase factor is going to evolve in a very, very interesting manner. So, psi of t is an eigenstate. Question is, does it satisfy the Schrödinger equation? Of course, we can't say that it does, because the time-dependent Schrödinger equation is this, right? And, you know, as you can see here, there's no way that psi of t, which satisfies this equation, must necessarily satisfy this. So the eigenstates need not satisfy the time-dependent Schrödinger equation, right? Might not solve it. So at first we propose an ansatz, okay, which is slightly wrong, but this is the first thing we try out. So we try out psi of t is equal to, so something like, okay, so this is the actual wave function we're looking for, and we're trying out, okay, let's look at eigenstate psi of t times by e to the I energy t over h bar, except that the energy is now changing in time, right? Now the point, here's the important point, the point is that you obtain this, so sort of this phase factor was obtained from doing, you know, from assuming the time. This phase factor was obtained from stationary states, right? Assuming that h didn't evolve in time. The key point is that when you differentiate this, you must get an energy out, right? Because, well, you know, because we want this d by dt to give you energy times psi. Right, we're looking for the wave function to satisfy this. So instead we replace this by an integral. Okay, the integral over the energy. And indeed, if you differentiate with respect to time, you're going to get the energy out. Okay, and with an IH bar coming out. Right, so this satisfies the Schrödinger equation, except we need to allow a constant, okay, which varies in time. Another possible degree of freedom. Now, if you plug this in, if you bung this into the Schrödinger equation, into this, and you work through the algebra, you get this equation right here. Okay? And this is a very simple separable differential equation. Okay, and this denotes the time derivative of psi. Okay? Now, what we do next is we dot it, so we multiply on the left by this ket vector, okay, of this entire equation. This is where we go slightly wrong, because in actuality, this psi of t, of course, is not going to be just a constant multiple of an eigenstate. In general, it'll be a linear combination of them, because that, you know, saying that this has to be psi of t would be like saying that a randomly chosen, you know, vector in R3, an arbitrary chosen vector in R3 must be just a constant times E1. No, you know, it's going to be a linear combination of all the bases, right? It's going to be a linear combination of the basis vectors. Or alternatively, you know, you could also say that the mistake comes in at this step, because actually, if we were to imagine this as a linear combination of all the actual eigenstates, you'd be picking out a particular component, right? You'd be just looking at the x component and all that. So actually, we're going to replace this with a sum, right? Which is obviously the reasonable thing to do, right? And that's what we always do, that's what we always do anyway. So anyway, when we solve this, right, we get a solution for c of t, and that's given by some constant c naught, which we kind of forget about, times this. Okay? And s will be the integration variable. Now note that this is purely imaginary. So this quantity right here is purely imaginary. Right? The way to check this, of course, is to take the complex conjugate and show that you get minus of this. Okay, so show this. So to do this, you actually have to compute this, right? You have to write it out. There are L2 functions. So essentially, this is integral over space, right, over the spatial, over space, of complex conjugate of psi d psi by dt. And you can rewrite this as the product of d by dt of psi star minus psi star, minus psi times d psi star dt. Okay, you can rewrite it like that. Now this is this gives you 0 because psi is normalized, right? So in particular, it's a constant, and so you get negative of this. So it's kind of like doing an integration by parts, right? That's another alternative way to get the result. Okay, you're essentially replacing AB dot with minus A dot B. Anyway, so we have that this is purely imaginary, okay? And essentially what we end up with is that the solution to the Schrödinger equation is given by psi of t is equal to e to the minus I over h bar integral from 0 to t of es ds times e to the I times I. It's just for notational convenience to write it like that, times ds, and then times, of course, an eigenstate. Of course, this is wrong, right? Because if this was, because we didn't input anything about, we didn't actually input the fact that our Hamiltonian was slowly varying. This would be an exact solution. Again, we went wrong by assuming this ansatz. Okay, but what we've really figured out, what we've actually figured out, is the following. So let me state it as the adiabatic theorem. Okay, so we've basically, so this isn't quite everything yet, but what we said is the following. What we've actually discovered is the following, somewhat. So I'll state the adiabatic theorem, which will require proof. So suppose that psi, the actual wave function, right, starts off in the nth eigenstate at time t is equal to 0, right, and the Hamiltonian is very slowly moving. So let's say that the time scale at which the Hamiltonian changes is given by t. Okay. Now, the adiabatic theorem states, and this is the bit that requires proof, that the actual wave function at time t, okay, so this is a very precise statement, but basically it's saying that we are very close to, so the adiabatic theorem states this, so let me write it out. Okay, so this is saying that essentially the true wave function is very, very, very close to the wave function if it were to stay in the eigenstate you started off with. So this is saying that, you're very, very likely to stay in the eigenstate that you start off with. So if you start off at the nth eigenstate, you're very likely to remain in the nth eigenstate. And this is actually more precise as to what we mean by very likely. Okay? Now, furthermore, the important thing is that this psi tilde n of t, that is not the same as this guy, right? So we're not saying that you're going to be very close, that the actual wave function is going to be very close to the initial wave function. Instead, it is going to evolve in time, but it's going to pick up a phase factor. Okay, and the phase factor is what all the calculation, if you work through it, gives you. So where psi n tilde of t is given by e to the I into phi n of t plus gamma n of t times by psi n of t. Okay, where psi n of t is the eigenstate. Okay, it's an eigenstate, and it solves h psi is equal to e psi, where h and e are functions of time. Okay, where theta of theta of t is the very boring one, so it's the factor that we always know we pick up, right? It's just the integral of energy, right? So that when you differentiate, you get energy back. But then this gamma n of t is when we solved for c, right, essentially. And that is given by the integral from 0 to t of I times nu n of s ds, where nu n is equal to the inner product of psi n, the inner product of psi n dot with psi n, where this is the time derivative. Okay, and this requires some computation. Okay, because remember that these aren't necessarily orthogonal to each other. Okay, and this right here, so this phase factor is, is kind of a boring one. It, as you increase time, it changes more and more. It's like a clock, right? It basically evolves as you bring forward time. But this guy right here turns out to have a geometric interpretation, i.e. that it is essentially independent of time. Now what we mean by this is we obviously make that more precise. Okay? So essentially, okay, so now I'm gonna really go through the summary here. But this is sort of how we think about nu n, right? So suppose that the Hamiltonian depends on a set of parameters which I give the letter r. It doesn't have to just be position. Okay? Now, what we do is we make r actually a function of time, right? Because the parameters, we imagine that the parameters change in time. Okay? So what we have got is h r of t psi n of r of t is equal to e n, which is a function of r of t, times by the vector psi n, which is a function of r, which is a function of t. Okay, so this is how we this is how we reimagine what the Hamiltonian looks like. Again, so this could represent, for example, angular frequency, right? The effective spring constant, and also it could represent, an effective mass or something that's changing in time. It could represent position, etc., etc. Okay? Now the way we think about this is that we imagine looking at the parameters, right? And at some moment in time, it's going to be a point. But as we run time forward, it's going to, produce a trajectory, right? So essentially, the Hamiltonian is kind of like a vector. You can imagine the Hamiltonian as a vector. And in fact, in the research paper, the Hamiltonian kind of boils down to. So I'll state this. The Hamiltonian simply sort of boils down to, the 2x2 Hamiltonian, without loss of generality, boils down to a minus a, so that it's traceless, and then b, b. Okay, where a, b are real numbers. And what they say is that they introduce two new parameters, h theta. Basically, they swap to polar coordinates, h cos theta and b sine theta. And so the way that we imagine this in 2 dimensions is that the parameters in this case would just be b and a, and this new polar coordinates would just, point here would just be h, and then this would be theta, right? And this would, this would change in time, so you'd have sort of a trajectory here. Okay, so this is what they mean by having actually a Hamiltonian being itself kind of a vector. But anyway, when we visualize it like this, right? If we focus on what nu n is, right? Nu n of t is I into psi n of r of t times d by dt of psi n of r of t, right? Because this was psi n dot. Now, the important point is that you're basically taking a total time derivative, right? So by the chain rule, this is actually just going to be, so I'm just going to skip a little bit the notation. Basically, it's going to be this, okay? And this dotted with dr by dt, where r is a, is a vector representing all the parameters. Now, gamma n of t is the integral of this from 0 to time t, and this would be t tilde, t tilde, t delta, dt tilde. And the important point, this is where the entire interpretation of this being geometric comes in. These cancel. So actually, the result of gamma depends on the path, right? It actually depends on just the path you take in this space. Okay, so this geometric phase that you pick up, gamma n of t, only depends on the path you take in this space of parameters. So if we were here, right, you'd be calculating just a line integral going from this point to this point, for example, right? So that's essentially why gamma is, gamma is nothing but a geometric phase. And is there anything else to be said? No. Okay, that's where I'll stop. So I'll stop there.